Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class. I'm also putting it online in case it would be helpful to others as well. In this section, we are going to discuss the derivatives of the 6 basic trigonometric functions, which is exciting. Now, if you are one of my students, you should have a printed set of guided notes that you can complete while we do this video. If you're not one of my students, there is a link to those notes in the description of the video if you would like to use them. Also, if you are one of my students, we have already had a discussion about what the derivatives of sine and cosine are. But just for those who missed that discussion, let me show you something kind of cool. If I go to my, I just have like a TI 83 plus calculator here. I don't have any of those 89s or fancier ones. So if I want to take a function and try to figure out what its derivative is, I kind of have to do this little old school thing with it where I try to apply the limit definition of derivative in a graph. Watch this. Okay, what I'm going to do is I want to know what the derivative of sine is. So I'm going to take sine of x plus a very small amount. I'm going to subtract from that sine of x, and then I'm going to divide that difference by that very small amount again. What that's doing is it is approximating the limit as h approaches 0 of sine of x plus h minus sine of x all over h, which is the sine of x function in the definition of derivative. So watch what happens when I graph. And by the way, I'm going to do a Zoom 7 trig viewing window. Oh, I think this is so cool. Okay, so you do the sine function like this, but what you get out, that's not the graph of sine, that's the graph of cosine. Oh, there's a bell. That's what happens when you're in a school. There's bells sometimes. Which tells us that the derivative of sine of x is cosine of x. That's nice, right? Nice and easy to remember. Now, toward the bottom of this page on this next slide, I prove it. What we were doing in the calculator was just approximating it, I guess. Now, I am not going to take the time in this video to go over all of that. It is here, and if you're one of my students, we will discuss it later on. But yeah, not in this video. Okay, we're just going to let that go. But this is the proof of the derivative of sine. Okay. Next, what's the derivative of cosine? If the derivative of sine is cosine, is the derivative of cosine sine? Well, let's check it out. We can go back into y1 and change those sines to cosines to simulate or approximate the derivative of cosine with a graph. What we hope to see is the graph of sine. We see a wave that looks like the sine wave here, right? But there's one major difference, and it's this. All of the y coordinates are opposite of what they should be. Meaning, this is pi over 2, and sine of pi over 2 is 1, but here it's negative 1. This is negative pi over 2, and sine of negative pi over 2 is negative 1, yet it's up here at 1. So what does that tell us? That tells us that the derivative of cosine is negative sine. Okay, not bad. You're just going to have to remember that negative there, which is kind of annoying, but oh, there's another bell. Isn't that wonderful? Okay, I think that'll be the last bell. Anyway, you'll have to remember that negative, but there will be negatives involved with other trig functions, as we'll see at the end of this video, so we'll just sort of have to keep that in mind. All right, so what I want to do now with example 1 is I just want to use the fact that we know the derivative of sine is cosine and we know the derivative of cosine is negative sine, and we want to do that with some other rules. Like, look at this function, y equals x squared sine of x. We are going to need to use here product rule, right? You have a x squared function times the sine x function, so once again, we will be using product rule to get our derivative. Now, the way that I like to remember product rule is 1d2 plus 2d1, which says take the first function times the derivative of the second function plus the second function times the derivative of the first function. That's too much to say. I'm going to stop saying that stuff, and I'm just going to say 1d2 plus 2d1. So I have 1 d2, the derivative of sine is cosine, plus 2, bring down the sign, d1, the derivative of x squared is 2x. Now, we're not going to do anything more with that except usually if you have something like this, you would have the 2x in front of the sign. That's not absolutely necessary, but it does kind of make it look a little bit better. Woo! Not too bad, right? Right. Look at this one now. It's not going to be too bad, I promise. All right, if u equals cosine of x over 1 minus sine x, we are to find du over dx and simplify. So we are to find the derivative of u with respect to x, the derivative of this using quotient rule, right? And then we will simplify. Now, I'm not going to write this little saying out, but you may remember that I like to say this for quotient rule. Quotient rule is low d high minus high d low, all over a low low. All right, so let's try it. Low is 1 minus sine x. D high, the derivative of cosine is negative sine. Let's put that in parentheses because of that negative. Minus high d low. The derivative of sine is, well, first of all, the derivative of 1 is 0, right? Okay. The derivative of sine is cosine, but there's a negative in front of this sine, so the derivative of negative sine is negative cosine. Does that make sense? The derivative of sine is cosine, therefore the derivative of negative sine is negative cosine. All over a low low means your denominator squared. Okay, so there's our derivative, but now we're going to clean it up a little bit, and we're going to use an important identity that just seems to pop up often, as you study math. The first thing, though, I'm going to do is distribute the negative sign through the parentheses in the first term. So I have a negative sine x plus sine squared x, because a negative sine x times a negative sine x is positive sine squared. Here I also have a plus, because a negative times a negative is positive, and it will be cosine squared x. Just bring along the denominator. At this step, I'd like to talk about that property that I was referring to. The property is, identity. Sine of x squared plus cosine of x squared is 1. This is called one of your Pythagorean identities, and it's one that we use a lot in this class, so I would be aware of it. And we can see that right here, right? We have a sine squared plus a cosine squared. So that all together is going to become 1. And now we have common factors in the numerator and denominator. Negative sine x plus 1 is the same thing as 1 minus sine x. So we can say that this factor, if we look at it as a factor of itself, and we have one in the denominator, we have 2 in the denominator, we can divide them out so that our simplified derivative can be written as 1 over 1 minus, not plus, sorry, 1 minus sine x. Yay, wasn't that beautiful? Now, Now the fun. Now that we are talking about derivatives of trig functions, we can have some fun with what is called simple harmonic motion. Okay, so here's a little definition of simple harmonic motion. It is periodic motion such as the vertical motion of a weight bobbing up and down at the end of a spring, which would be modeled by a sinusoidal position function. Okay, sinusoidal position function means the position function could be a sine or a cosine. Now, I have a little friend. Usually when I teach this lesson live or in person, we use the little mouse here, and oh my gosh, I forgot his name, and I'm so mad at myself now because we named him either last year or the year before, and it was a really good name, and I cannot remember it. I wish I would have looked it up because I think I have it somewhere. But anyway, he's our little mouse who models simple harmonic motion for us. I usually have him like in a setup where like he's being held up on one of those things that they use in physics class to hold a spring with a weight on it. I don't know what they're called, but he's being held up, and then I can like pull him and then let him bob up and down like that. And notice that he's going between one point and the other, so that could be modeled by a wave. Yay! This is working out all right, right? All right. I love this mouse. I've been using this mouse as a prop for years. And he's not my mouse. He is the physics, the AP physics teacher's mouse here at my school. And every year I come to her and I say, I'm about to teach simple harmonic motion. And she says, I will get the mouse. And I'm like, yay, there's the mouse. All right, let's go. Example 3, we have a weight hanging from a spring is stretched 5 units beyond its rest position, and that is, the rest position is called S equals 0, and released at time t equals 0 to bob up and down. Its position at any time later is given by this function, S of t equals 5 times cosine of t. The question is, what are its velocity and acceleration at time t, and describe its motion. All right, so I like to start this problem by drawing a little visual of what's going on. Okay, so we have something like a mouse, or, we could just use a block to show we have a weight on a spring. There we go, and here's our weight on our spring. Okay, and we have a few positions that are important here. We have rest position, which is S equals 0. Okay, so that's just when the weight is hanging without anything acting on it but gravity. Then we have the stretched position, which is what the problem says is happening at time 0. And I guess by the setup of this, I'm going to call that 5. Okay, stretched will be a position of 5. And okay, so what happens is the mouse is stretched 5 units beyond its rest position to start, and it's not just going to go back to the rest position, right? It is going to go up to what I call a retracted position. So we have stretched, we have rest, and then we have retracted. And so, I'm going to draw a little retracted position here, and I will label that as a -5 position. Okay, now the reason I know to use the numbers 5 and -5 for the stretched and retracted position, by the way, I'm going to label these with words: rest, stretched, it says stretched, and retracted, is because of what this 5 cosine of t function looks like. Okay, so let's just do one period here, and we'll use pi over 2, pi, 3 pi over 2, and 2 pi as different points in time. And then we have positive 5, negative 5. Okay, just to prove to you with the calculator, because sometimes we like to see that, 5 cosine of t, I'm going to use x. Oops, I did not mean to do that. I meant to do zoom 7 again. I guess I need to change my window slightly. At 0 is at positive 5. Okay, so we're starting here. At pi over 2 is at a position of 0. At pi is at a position of negative 5, and then it cycles back to that positive 5. So we have, again, at time t equals 0, we're at positive 5. And that's why I decided to define stretched at positive 5. Okay, at time t equals pi over 2, we're back to a position of 0. I should label this as position. And at time t equals pi, we are at negative 5, back up to 0 position at 3 pi over 2, and then a position of 5 back up to 2 pi. Now we have to try to draw the cosine wave through those points. Good luck with this tablet. Okay, not bad. I'm going to go with it. All right, so this graph could serve as a way to describe its motion verbally. We could say that the mouse is at stretch position of 5 units at t equals 0, retracted position at time t equals pi over 2, and so on. I'm not going to write all of that out right now, but what I do want to make sure to do before we move away from this problem is get the equations for the velocity and acceleration. Okay, so we talked about in a previous section that the first derivative of the position function is your velocity function. So this is where we're going to use the fact that we know that the derivative of sine is cosine. We know the derivative of cosine is negative sine. So the velocity would be negative 5 sine of t. The acceleration then is a second derivative, or a derivative of velocity. And once again, we know that the derivative of sine is cosine. So therefore, the derivative of negative 5 sine is negative 5 cosine. All right. Now that we are talking about periodic motion and simple harmonic motion and sines and cosines, we can actually talk about one more rate of change, and that is jerk. The rate of change of acceleration, if acceleration is changing, we call the rate of change of acceleration jerk. Okay, so jerk would be, in our sequence of functions, a third derivative. So this is s prime, this is s double prime, this is s triple prime. And now that you know that information, you can understand this joke. I mean, that's like the main reason we learn it. Don't be a what? Don't be a jerk. Now, it's using x instead of s, but we get the idea, right? And now here's sort of maybe a joke. I'm not quite sure if this is a joke or not. I've never nailed down like a really solid answer to this. Okay, so we know that we have position, and then a derivative of that is velocity, and then another derivative is acceleration, and now a third derivative is jerk. What happens after that? Fourth, fifth, sixth derivative, we call them snap, crackle, pop. I don't know. Okay, I tell my students that every year. They look at me like I'm crazy. I am crazy. I might be, making this up. I don't know, but I've heard that. All right, let's do a couple of examples with jerk. In example 4, it says find the jerk of the simple harmonic motion in example 3. So going back to example 3, we're just going to pick up where we left off. We had an acceleration of -5 cosine t. Actually, let's write it all out. It's not too much. We started with a position of 5 cosine t, a position function. We took a first derivative and we got velocity to be -5 sine t. We took a second derivative and we got acceleration to be -5 cosine t. Now think about this. What would be the next derivative that we're going to call jerk? Well, again, the derivative of sine is cosine. The derivative of cosine is negative sine. So if we have another negative in here, that's back to +5 sine t. Ooh. All right, here's a you try. So I would suggest at this moment you pause and you try it. And I'm going to put my work up and then I'll come back and show you. All right, here's an answer. So starting with a position of sine t plus cosine t, you can take a first derivative and keep in mind that the derivative of sine is cosine, the derivative of cosine is negative sine, and that gives you velocity. We were asked to find jerk of the body at time t equals pi over 2. So we need to do 2 more derivatives. You can see that I did those there, just being very careful of my signs, meaning positives and negatives, as I did derivatives. So the derivative of negative sine is, or the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, and so on. This is what you should get as your jerk function, or your third derivative. The derivative of negative sine is negative cosine, the derivative of negative cosine is positive sine. And then we were given a specific point in time, t equals pi over 2. And so I subbed that into my jerk function and evaluated. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 0 plus 1 is 1. Notice the units. We are in a third rate of change, so that is meters per second cubed. Okay, finally, the last thing we need to talk about are what are the derivatives of all of the other trig functions? We've focused a lot on sine and cosine. Well, the reason we focus so much on sine and cosine is because the other trig functions can be written in terms of sine and cosine, right? So here we're not going to write the derivatives of these trig functions, but we are going to write how we define these trig functions in terms of sine and cosine. So for example, tangent of x can be written as sine of x over cosine of x, right? Secant of x is the same as 1 over cosine of x. It's called the reciprocal function to cosine. Cotangent is the reciprocal to tangent, but instead of writing 1 over tangent, let's just flip what we have right here and write cosine of x over sine of x. And cosecant of x is the reciprocal of sine. It is defined as 1 over sine x. Now, we can use this information to figure out all of the other derivatives using quotient rule. If tangent can be written as a quotient of sine over cosine, and we know the derivative of sine, we know the derivative of cosine, and we know quotient rule, we can get the derivative of tangent. That's what we're going to do right here. Use y equals sine x over cosine x and differentiate using the quotient rule, and that will give us the derivative of tangent. Okay, so if we have y is equal to sine x over cosine x, that means that y prime is cosine x times cosine x, right? What am I doing here? I'm doing low d high minus high d low, which is negative sine. all over a low, we can write that as cosine squared x. Now let's simplify. We have cosine squared x plus sine squared x all over cosine squared x. Now, listen to me. Do not cross out these cosine squareds. You can't do that. I have students get to this point and they're just like, yeah, no. Okay, you can only divide out common factors. This is not a common factor in itself because it's attached to a plus sine squared. It's a term. Okay, but what can we do? We can change that entire numerator to 1, can't we? That's using that identity that says that sine squared plus cosine squared is equal to 1. Finally, here's how we typically remember the derivative of tangent of x. We will rewrite this instead of 1 over cosine x as secant squared x. Yay! So if you don't know the derivative of tangent, you can use the fact that it is sine over cosine and get the quotient rule. However, typically, we just sort of remember that the derivative of tangent x is secant squared x, so that we don't have to go through that work every single time. Now, you can use that quotient rule to get the derivatives of the other 3. I'm not going to do all of that here in this video, but we will be doing it in class together if you're one of my students. So you can do it here, low d high minus high d low over low low for secant x, and what you will get is secant x tangent x. Yeah. You can use cosine over sine and quotient rule to get the derivative of cotangent, and what you will get is negative cosecant squared x. Yes, you will. And finally, you can use 1 over sine with quotient rule, and you will get the derivative of cosecant x, which is negative I always do that. I always do that when I'm about to write cosecant. Negative cosecant x cotangent x. Yeah. So let me put the other ones out here that we already had. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Because I know this is a lot to, it feels like it's a lot to remember. However, I want to show you one little trick that makes it slightly easier, and it's this. The derivatives of all of the cofunctions, cosine, cotangent, cosecant, all of those are negative. Okay, I know it's not like a huge trick to help you remember them, but it's one thing. At least you can remember when is it supposed to be a positive derivative, when's it supposed to be a negative derivative. The rest will come, I promise you, because throughout the rest of the chapter, you are going to be doing the derivatives of these over and over and over again. And so if you actually do practice them, you will remember them. Let's practice right now with this last example. Find y double prime if y equals secant x. Okay, well, to find y prime, we can just look at the information above and say, okay, the derivative of secant x is secant x tangent x. But now, to get y double prime, do not just take the derivative of secant times the derivative of tangent. This is product rule. One d2 plus 2d1. So the first function comes down, and we multiply by the derivative of the second function, which is tangent. That derivative is right here, secant squared. There's 1d2 plus 2d1. The second function comes down, and we multiply it with the derivative of the first function. Once again, the derivative of secant x is secant x tangent x. Finally, simplify slightly. We have secant cubed x plus secant x tangent squared x as our second derivative answer. Yay! As usual, I hope this video was helpful, and good luck in your studies. Bye.